Hello, on this module we'll cover a brief overview on thermoplastics. The aim of this module will be to review some important concepts regarding polymers. Why will we do this? It's important in understanding how these properties and characteristics will affect the processing and your final product. With this information, you can be in a better place to interpret your inputs and the final results from your analysis. Plastics are what we call polymers. This comes from a Greek word, polymer, where poly means many and mer means parts. So it's many parts. If you were to visualize this, a polymer molecule is essentially a long chain of repeating units. There are two main polymer classifications, thermoplastics and thermosets. Thermoplastics, they come from a Greek word as well, therm, which means heat, and plastikos, which means capable of being molded. Thermoplastics, that's what we'll focus on mainly in these modules. And the differentiator here is that thermoplastics can be formed and reformed, allowing us to recycle them. Of course, there are some properties that are lost during this process, but it is something we can do nonetheless. Thermosets, on the other hand, they are from a Greek word that means therm, again heat, and sets, irreversible when heated. So, as one might assume, thermosets, they cannot be remelted. When they are formed, they undergo a chemical reaction or a cross-linking, and they can no longer be remelted and recycled. If you try to do this, they typically just burn. Polymers can also be classified based on their morphology. The main ones we typically discuss in industry are amorphous and semicrystalline. So, an amorphous arrangement of molecules has no long-range order or form in which the polymer chains arrange themselves. So basically we were thinking of a plate of spaghetti would be a good example here. We have the same molecular structure throughout the molding cycle. So as you heat the polymer, you cool the polymer, you're still left with this plate of spaghetti essentially in front of you. Amorphous polymers are typically transparent, which is a very important characteristic for many applications such as food wrap, plastic windows, headlights, and even contact lenses. Our second classification based on morphology could be semicrystalline materials. Now, typically when we think about crystalline structures, we're talking about thinking about salt or gemstones, and not maybe plastics, but plastics, semicrystalline plastics do have crystalline arrangement, or can. So this degree to which the crystallization occurs will depend on how the plastic cools and the history in the molding cycle. So this can be very important with our mechanical properties, but the most obvious is typically you could see in the clarity of it. So the higher degree of crystallinity, naturally the more crystals that have formed in there, it will allow less light to pass through that polymer. So it's directly affected by crystallinity, even from a visual aspect. When talking about plastics and processing them and simulating them even, there are several properties of interest, and these range from processing conditions such as mold and melt temperature, which are important to optimize and capture, rheological properties in your material, things such as viscosity or juncture loss coefficients, transition temperatures. We have thermal properties as well, so specific heat, thermal conductivity, physical properties, mechanical properties, and even shrinkage properties. These are all things that are utilized and we do account for within the software. Now we'll take a closer look at some of the most common processing conditions. One is mold temperature, which is a temperature of mold where the resin touches the mold. Melt temperature, that's the temperature of the resin or the melt as it actually begins to enter the cavity. Ejection temperature, this is a temperature at which the material is rigid enough to withstand ejection. This is different from the transition temperature. the maximum shear stress. Of course, this is the shear stress for that material that you want to stay within. If you exceed that, then you may start to see some degradation in your material's properties. The maximum shear rate is the shear rate at which the material will degrade as well. So if we want to look at shear stress and shear rate, think of a polymer as flowing in many layers. It's in laminar flow. So the shear stress is essentially the force being exerted between those layers. The shear rate is how fast those layers are sliding past one another. So these can lead to shear heating. They can also lead to degradation of your material's properties, as I had previously mentioned. So these are two important values that the software will make you aware of, but you also want to know what the proper values are for the material working with, since they will vary. We'll now take a look at some of the common rheological properties that you should be familiar with. One is viscosity, and that's simply the material's resistance to flow. Juncture loss method coefficients. These are the calculation of hydraulic loss that occurs when the melt passes through a large channel in path diameter. So, for example, your converging flow coming through a gate. This helps us to accurately capture pressures. Transition temperature, which is simply the temperature to which a polymer freezes. So it's the exact point in which the polymer starts going from a molten state to a solid state. The melt flow rate, or some may call it an MFR number, this is basically an industry standard test which measures how easily the melt flows. And the way this runs is there's a given die with a diameter, and we apply a certain pressure at the top of this die to force the plastic through it. We time this over a 10-minute period and simply see how many grams come out the bottom of that die. So it's typically measured in grams per 10 minutes. So you could have 5 grams per 10 minutes come out of the bottom of that die for high viscosity materials, or 10 grams per 10 minutes come out of that bottom of that die for maybe a lower viscosity material. It's important to note that your material's viscosity can be influenced significantly by shear rate and temperature. So polymers typically flow much easier when they're sheared. They also typically see a decrease in viscosity when the temperature for that polymer is increased. So this is very important for thin-walled applications, because thin-walled applications you would typically see higher shear rates, which could lower the viscosity of your material, but you have to be aware of those shear rates and make sure they are not exceeding the material's limitations. You can see here in the graph an example of that. We can also see where a polymer kind of places in the viscosity relative to water and glass. It's somewhere between there. Some common thermal properties that we should be aware of are specific heat. It's the ability to hold heat. So it's basically a measure of a material's ability to convert a heat input to an actual temperature increase. The internal energy curve is normally almost linear, so it can be approximated by measuring the heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius, or 1 degree Kelvin. Thermal conductivity is the ability to conduct heat, or the measure of a rate at which a material can dissipate heat. Thermal diffusivity, or the ratio of thermal conductivity to heat capacity. And substances with a high thermal diffusivity will rapidly adjust their temperature to that of their surroundings, because they conduct heat quickly in comparison to what we would call their thermal bulk. So in the previous slide you may ask, well, why do I care about these mechanical properties for my polymer? Well, here's your answer. The impact of a material, or these properties, can have an impact on your cooling time essentially. So cooling time is based on the thermal conductivity, density, and specific heat of a resin. These combine to create what we call the thermal diffusivity of the material. So, as you can see here, our thermal conductivity. As that is increased, our cooling time decreases. As it decreases, our cooling time can increase. Specific heat, as that increases, our cooling time increases. As that decreases, our cooling time can decrease. And then density, you can see, has a similar effect as the specific heat. So this does impact our cooling times, so naturally it impacts our cycle time. Now we'll talk about some of the common physical properties of a polymer. So one is the melt density, which is just as you might assume, the density of a material in its molten state. The solid density, which is just the density of that material in its solid state. And then we also have the specific volume, which is typically captured by a PVT diagram. This diagram is basically going to illustrate or show us how the temperature-pressure relationship for polymers over the entire processing range. So it shows us a relationship between temperature and pressure on the specific volume of a material. Here's a good example of what a typical PVT diagram might look like. So the PVT diagram, as we mentioned briefly before, it's going to show how a plastic contracts or expands as the pressure and temperature change. So if you think of something like a marshmallow, if we heat that marshmallow up, it will likely expand. It'll occupy more volume. If we apply pressure to something, let's say a sponge, that pressure, the sponge will actually decrease in the specific volume or the volume it is occupying. So typically as pressure increases, our volume is decreasing, and the PVT diagram is the way that we can capture how, as I mentioned, the plastics are contracting and expanding with different pressures and temperatures. Very important relationship to capture. The PVT diagram also gives us the opportunity to capture a unique transition that happens in amorphous and crystalline or semi-crystalline materials. So with amorphous materials, this transition corresponds to the glass transition temperature. So on the left, this is an amorphous material PVT diagram, and you'll see the slope is somewhat gradual, and then at a certain point in time there, somewhere around, let's say 90 degrees Celsius, we see a sudden increase in the slope of that curve. That point in which the slope changes is going to be our glass transition temperature for an amorphous material. For crystalline materials or semi-crystalline materials, we call this transition the crystallization temperature. So you can also see how that curve changes significantly towards the 250 degrees Celsius point on the curve on the right. That changing point right there is what we would call the crystallization temperature. So some common mechanical properties we'll discuss will be the elastic modulus, which is the force you need to provide to elongate the material. So essentially how flexible a material is. Shear modulus, which is a ratio of shear stress to shearing strain within the proportional limit of the material. And then Poisson's ratio, which is a ratio of the lateral to axial strains. This is also used to relate shear and elastic modulus. The transverse isotropic coefficient of thermal expansion, or CTE data, that's definitely a mouthful, but we commonly just call it CTE data. And what this is really showing us is how a material expands and contracts based off of temperature changes. And we can combine this CTE data with the mechanical data, other mechanical data, to account for the variation in properties parallel and perpendicular to the direction of flow. So polymers, as they're injected, we have a molecular orientation or a fiber orientation. This, of course, induces what we call anisotropic material properties, or properties that are different in each direction. So when we use the CTE data and the mechanical data, this is very important to have it tested and accurately in your material if you're interested in deflection results, because these play a huge role in that. Now we'll discuss some of the shrinkage properties in more detail. This is not something that you'll see for all the materials in the database, but if you do see it, that means that this material has been tested for CRIMS data or shrinkage data. And what that does is it's a specific test in which we run a DOE, or a design of experiments, which allows us to catch the interaction of several different combinations of process settings and see how that impacts the shrinkage of that material. Now, if you're looking at the shrinkage properties, you may notice that there are 3 shrinkage models to choose from. We have the residual strain, the uncorrected residual stress, or the corrected residual in-mold stress, which we call CRIMS for short. The differentiator between these 3 is that the residual strain and the CRIMS models, they both have some degree of shrinkage data or shrinkage testing that have been done to that material. The uncorrected residual stress does not have any shrinkage data to it, so when you run this model in mid-plane or dual domain, it will be purely theoretical. If your material has residual strain or the CRIMS model available and you're running in mid-plane or dual domain, then this can be expected to add accuracy to your warpage calculations. You may ask which is the best to use. Well, we've done that work for you. The best shrinkage model is typically set by default, so this is not something you would typically change. Some of the other values you might see within the shrinkage properties would be the observed nominal shrinkage. This is basically the average shrinkage value parallel and perpendicular to the direction of flow. And these values, of course, were obtained during our shrinkage testing that we did. The observed shrinkage, that is basically the max and min values for shrinkage that we notice parallel and perpendicular to the direction of flow during our shrinkage analysis. So you may see these in there. It's just for your reference, and if you look even further down, you'll notice that we actually have the specific test data sets and values if you were that curious. Now for a quick knowledge test. What are the main polymer classifications covered during this presentation? Please choose all that apply. Name 2 of the classifications based on morphology that we discussed earlier in this presentation. Thermoplastic materials can be heated and reformed over and over again even after the polymer is formed, which allows recycling. Is this true or false? The best shrinkage model is typically set by default for a tested material. True or false? What kind of graph is shown in the following image?